When you translate a paragraph of English into Spanish, you can't just open a dictionary and swap the words out one for one.
Right, because a direct mapping like that usually ends up sounding like absolute nonsense.
Exactly. To make the translation actually flow, to capture the nuance and the idiom, you basically have to break that original sentence down into pure meaning.
Yeah, you sort of strip away the English grammar entirely.
Right. You hold the abstract intent in your mind and then rebuild it from the ground up using the rules of the new language.
And that intermediary space is just fascinating to me. It's this hidden realm where structure is completely dissolved.
Leaving nothing but raw logical intent.
Exactly, just waiting to be remolded.
And that hidden realm is exactly what we are exploring for you today in this deep dive into your Class 21 compiler design notes.
Yeah, we are pulling specifically from chapters 8 and 12 of Introduction to Compilers and Language Design.
We're stepping into the hidden middle of a compiler. So this concept known as the intermediate representation, or IR, we're going to look at the mechanisms, the actual magic tricks, really, that transform human-readable code into highly optimized, blistering fast machine logic.
But, to appreciate how that transformation happens, we really need to map out where we currently stand in the Unix compiler lifecycle.
Okay, set the stage for us.
Well, at this point in your project, you've already taken in the raw character stream. The scanner tokenized it. The parser checked the syntax and generated your abstract syntax tree, the AST.
Right, the AST.
Yeah, and you've even run the semantic routines to check the static semantics.
So I have this fully validated tree that perfectly represents the logic I typed into my text editor.
Exactly.
My instinct tells me the compiler should just, hand that tree straight over to the code generator and spit out the final assembly code.
Sure, that makes intuitive sense.
But instead, the notes mention this intermediate phase, the IR and the optimizer. And interestingly, it's technically optional.
It is optional, yeah.
I could skip it entirely and still get a working executable. So why on earth would I want to add this massive layer of complexity?
Well, we add that complexity because of the physical realities of the von Neumann architecture.
Okay, what does that mean in practice?
So the machines we write code for suffer from a fundamental physical bottleneck. It's this eternal battle between a lightning-fast CPU and a painfully slow main memory.
Ah, right. CPU versus RAM.
Exactly. To put the speed difference into perspective, the CPU can perform thousands of arithmetic operations in the exact same amount of time it takes to fetch a single integer from RAM.
Thousands to one. Wow.
Yeah.
If I'm thinking about that in human terms, if an arithmetic operation inside the CPU takes 1 second,
Right.
then fetching a variable from memory is like walking for almost an hour just to read a number off a piece of paper.
That translates perfectly to the physical constraints of the hardware, actually.
An hour walk for one number.
Yeah, so the optimizer's entire job is to mitigate that hour-long walk. We want to generate an executable that minimizes memory fetches, strips out redundant instructions, and, carefully hoards data inside the CPU's ultra-fast registers.
Because those registers are super limited.
Very limited. And the intermediate representation is the specialized vehicle that makes those heavy optimizations possible.
Okay, let's unpack the mechanics of that. Because if I already have this beautiful abstract syntax tree from the parser,
Yeah.
why do I need to invent a whole new intermediate representation? Why can't the compiler just run its optimization algorithms directly on the AST?
Well, what's fascinating here is that the AST is actually a victim of its own richness.
A victim of its richness.
Yeah, it is a fantastic, highly detailed representation of what the programmer typed. But it is entirely too complex for an algorithm to easily analyze for inefficiencies.
Okay, how so?
An AST has dozens of different types of nodes. You've got if statements, while loops, variable declarations, and it is heavily optimized for top-down traversal.
Oh, I see. It's like a highly detailed architectural blueprint of a house.
Exactly.
That blueprint is great if you want to understand the layout of the rooms or where the doors are, but it's terrible if you're the plumber trying to figure out the most mathematically efficient way to run a water pipe from the basement to the 3rd floor.
Right. The plumber doesn't care about the wallpaper or the crown molding.
No, they just need to see the structural voids.
Exactly. The AST simply carries too much high-level baggage from your source language, whether that's C, Java, or B minor.
So it's just too cluttered.
Way too cluttered. To identify deep optimization opportunities, the compiler needs to flatten that structure into something much simpler.
Something more uniform.
Right. Something highly uniform that sits comfortably between high-level concepts and raw CPU instructions. And crucially, this simpler structure needs to be easily serialized into plain text.
Why does it need to be plain text?
So it can be passed sequentially through different independent optimization algorithms.
Oh, okay. Which brings us to the star of Chapter 8 in your notes. The directed acyclic graph, or the DAG.
The DAG, yes.
Now, looking at the diagrams in the textbook, a DAG looks, well, a whole lot like an AST at first glance.
It does look very similar.
It has nodes, it has branching paths, but the fundamental difference is in how the branches interact at the bottom of the structure, right?
Exactly. In a standard AST, every single operation you type creates a brand new divergent branch.
Even if you're doing the exact same thing?
Yep. Even if you're repeating the exact same math problem, the tree just branches out wider and wider. A DAG, however, allows for converging branches.
Converging, so they come back together.
Right. It allows multiple parts of your code to point to the exact same shared node to avoid duplication. The leaf nodes represent your ultimate values or variables, and the internal nodes represent the specific operations performed on them.
I want to walk through the specific example from the Class 21 notes to see how this physically works.
Sure.
Say I write the code x equals, in parentheses, a plus 10 times, in parentheses, a plus 10.
Okay, a classic example.
In a normal AST, the tree would calculate a plus 10 on the left side of the multiplication, and then it would just blindly create a completely separate duplicate subtree to calculate a plus 10 again on the right side.
It literally makes the processor do the exact same work twice.
Right. So the DAG avoids that entirely.
It avoids it entirely through a mechanism called the value number method.
Value number method.
Yeah. Instead of a top-down approach, the compiler performs a post-order traversal. It starts at the very bottom leaves of the AST and works its way up.
Okay.
As it builds the DAG, it maintains a specialized hash table.
Ah, so it's caching its work.
Exactly.
If I'm understanding this right, it takes the operation, say, addition, and it takes the memory addresses of the two child nodes A and 10.
Right.
And it hashes them together to create a unique fingerprint for that specific math problem.
It creates a unique row in the table for every single operation. So before the compiler adds a new internal node to the DAG, it hashes the proposed operation and instantly checks the table.
And if it finds a match.
If it finds a match, meaning it has already built a node that adds a nan, it halts. It refuses to create a new node.
Wow.
Instead, it just draws a line from your current location back down to the existing node.
It just points to the receipt of the problem it already solved.
Precisely.
So for a multiplication problem, both the left side and the right side point down to the exact same single internal addition node.
Yes. You compute a plus 10 once, store it in a CPU register, and just multiply that register by itself.
The savings in CPU cycles must be massive over a large code base.
Oh, the performance gains are substantial. And the DAG goes even further when we factor in static semantics.
How so?
Well, an AST usually just decorates a node with a label noting its data type. But the DAG actively modifies its own physical structure based on the data types it encounters.
Preparing itself for the hardware.
Exactly. Preparing itself for the reality of the silicon.
I saw this in the notes, and the mechanism behind it is fascinating. Say we go back to our a plus 10 example. The compiler suddenly discovers that variable A is actually a floating point number, like 3.14, but the 10 is an integer.
Right. That's a problem. The physical arithmetic logic unit inside the CPU cannot directly add an integer to a floating point number.
Because they're encoded differently.
Completely differently in binary. So the DAG intercepts this mismatch. It inserts a brand new hardware-specific node just for the 10 called ITO.
Enter to float.
Enter to float, yeah.
Right.
It forces the 10 to become 10.0. Then it swaps out the standard integer addition and multiplication nodes for FADD on FMUL.
FADD and FMUL. So it replaces the operations with the specific instructions required to fire up the dedicated floating point processor on the chip.
You got it.
The DAG is literally reshaping your abstract logic to match the physical architecture of the hardware. That is so cool.
It really is. And once you have this highly accurate, completely non-repetitive DAG, the setup phase is complete.
Ready for the heavy lifting.
Exactly. Now, the compiler can serialize it into a succinct text format and start running it through the aggressive optimization modules described in Chapter 12.
This is where we get into the magic tricks.
The one stuff.
Yeah. So what do we actually do with this highly refined DAG? I'm looking at the first major optimization. Constant folding.
Constant folding.
So textbook gives the classic example of calculating seconds in a day. You know, a programmer writing readable code won't just type 86400.
No, that's a magic number. It's bad practice.
Right. They'll write seconds per day equals 60 times 60 times 24.
And if the compiler simply generated assembly for that literal string of text, the CPU would be forced to load 3 separate constants from slow memory.
The hour-long walk.
Yes, and push them through the multiplier circuit twice every single time that line of code executed. Inside a loop, that's a catastrophic waste of time.
Let me guess how constant folding fixes this. Because the DAG is simplified, the compiler scans it, finds an operator node where both children are literal constants like 60 and 60. And it literally just does the middle school math itself during compile time.
Exactly.
It collapses those 3 nodes into a single node holding 3,600.
Yeah.
Then it sees 3,600 times 24 and collapses that down to 806,400.
It executes your code partially before the program ever leaves your computer.
That's brilliant.
If we connect this to the bigger picture, the implications for software engineering are profound. You can write incredibly verbose, self-documenting code using named constants and elaborate mathematical expressions, and you suffer 0 performance penalty at runtime.
So the compiler just absorbs all the overhead for you.
Completely.
That's a huge relief. And it doesn't stop at just folding constants together. We also have strength reduction.
Strength reduction, yes.
Which sounds like a gym routine, but it's actually about intercepting heavy CPU operations and swapping them out for physically lighter ones.
Right, because not all arithmetic operations take the same amount of physical time inside a processor. Consider the expression pow of x comma 2, which calculates x to the power of 2. In high-level code, calling that power function usually invokes a massive mathematical library that might calculate a Taylor series to arrive at the answer.
Oh, wow.
It's incredibly cycle-heavy. Strength reduction spots that pattern in the DAG and simply overwrites it with a basic x times x multiplication node.
It swaps a sledgehammer for a scalpel.
Exactly.
The notes give another great hardware-level example, multiplying a variable by 8. Instead of sending x and 8 into the multiplication unit, the compiler intercepts it and changes it to a bitwise left shift, x left shift 3.
Yes, the bitwise shift.
I love the physical reality of this. A bitwise shift just routes the electrical signals down adjacent wires to slide the binary zeros over.
It's so elegant.
It takes almost 0 time compared to firing up the massive grid of logic gates required for a full multiplication algorithm.
You achieve the exact same mathematical result, but you bypass the expensive hardware entirely.
I have to ask though, so what does this all mean for the programmer?
What do you mean?
Like, does this let us off the hook? Can I just write lazy, terrible code and assume the compiler will act like a digital janitor walking behind me and cleaning up my mess?
Oh, absolutely not. That is the most dangerous trap a developer can fall into.
Good to know.
The compiler is undeniably clever, but it has 0 creativity. It can only apply these optimizations to highly localized, recognizable mathematical patterns.
So it can't fix bad design.
No. If you write an algorithm that runs in O of n squared time when it could be solved in O of n time, the compiler cannot fix your logic.
It just makes bad logic run slightly faster.
Exactly. It will just make your terrible O of n squared algorithm run a tiny bit faster. Writing logically sound, fundamentally efficient code from first principles is still entirely required. The digital janitor cannot rebuild the foundation of a poorly designed house.
Fair enough. The foundational logic is still on us.
Always.
Okay, let's look at another optimization that just blew my mind because it messes with the actual fabric of time in our programs. Instruction reordering.
Oh, this is a fun one. To understand why reordering is necessary, we have to look at how a modern CPU pipeline physically works.
Okay, lay it out for us.
A CPU doesn't just execute one instruction, finish it completely, and then look at the next one. It acts like an assembly line in a factory.
Right.
It fetches one instruction, decodes the second, executes a third, and writes back a fourth, all simultaneously.
But if an assembly line needs a specific part, say, a piece of data from main memory, and that part hasn't arrived yet, the whole line has to start.
Exactly. The CPU stalls. It just sits there vibrating, doing nothing for hundreds of cycles, waiting for memory.
Just burning time.
Right. So to prevent those stalls, the compiler analyzes your DAG and deliberately scrambles the order of your instructions.
Wait, it changes the order I wrote them in?
Yes. If instruction A is stalled, waiting for memory, the compiler will grab instruction C, which has nothing to do with A, and feed it into the pipeline to keep the hardware busy.
The notes have a great, simple example of this. We have 4 variables. First, x equals 15. Then, y equals x plus 13. Next, z equals y times 20. And finally, a equals x plus y.
Right. A very standard sequence.
Based on the math, z desperately needs y to finish computing. But a only needs X and Y. So the compiler could completely reorganize my code to calculate A before it calculates Z simply because the ingredients for A might be ready in the register sooner.
Exactly. It safely violates the chronological order of your source code to achieve maximum throughput.
But wait, if you start shuffling a deck of variables, how does the compiler not lose track of what value belongs where?
What do you mean?
Like if I have a loop where the variable X is updated 10 different times, how does the compiler know which specific version of X goes with which instruction when it's throwing things out of order?
That exact dependency nightmare is why compilers convert the DAG into a form called static single assignment, or SSA.
Static single assignment.
Yes. SSA introduces one unbreakable rule to your intermediate representation. A variable name can only be assigned a value exactly once. It can never, ever be modified.
That sounds impossible. The whole point of a variable is that it varies. I mean, I increment counters and loops constantly.
In your source code, yes, you do. But when the compiler translates it to SSA form, every single time a variable gets a new value, it gets a completely new name.
Oh, wow.
Yeah, your first X is labeled by 1. When you update it, the compiler doesn't overwrite it. It creates by 2. The next update becomes by 3.
Oh, I see. It creates a permanent historical record, like a fossil record of every state that variable has ever occupied.
Exactly. And by doing that, the dependencies become perfectly clear.
Right, because if instruction Z needs by 2, the compiler knows it can move Z absolutely anywhere in the pipeline as long as it happens chronologically after by 2 is minted.
The ambiguity is completely destroyed. This makes it trivial for the compiler like the GNU-C compiler, which uses this, by the way, to see exactly which statements depend on which variables, allowing for safe reordering.
That is so smart. But wait, I'm thinking of an edge case here.
Okay, let's hear it.
What about branching paths? If you have an if-else statement, and X becomes by 1 in the if block, but it becomes by 2 in the else block.
Right.
What happens when the two paths merge back together? Which version of X does the rest of the program use? If we don't know which path executed until runtime, how does the static compiler know which number to assign?
That is a very perceptive question. SSA solves this by introducing something called a phi function at the exact point where the control flow merges.
A phi function.
Yeah, PHI. The phi function basically says, I will look at the path the program actually took at runtime, and I will dynamically select either by 1 or by 2 and output it as a brand new variable by 3.
Oh, that's wild.
It acts as a logical traffic cop, ensuring the unbroken chain of unique assignments continues safely down the rest of the program.
That is an incredibly elegant solution. And the notes actually point out that if you're using the GNU-C compiler, you can peek behind the curtain.
You can, yeah.
If you compile your code with the -f dump tree optimized flag, GCC will literally dump its internal SSA representations right onto your screen. You can read the by 1 and by 2 variables and watch the compiler thinking out loud.
Viewing those dump files is highly recommended. It takes the mysticism out of the compiler and shows you the raw mechanical logic at work.
Okay, so we have DAGs hashing out redundant math, constant folding doing our homework, strength reduction dodging heavy hardware, and SSA untangling time and space.
It's a lot.
This all sounds like a superpower. Why on earth wouldn't we want this running constantly? I mean, the notes note a surprising fact from Chapter 12. Most compilers do not run these optimizations by default.
That's right, they don't.
You have to manually enable them. Why leave free performance on the table?
Well, it comes down to two major compromises: compile time and developer sanity.
Okay, let's start with compile time.
First, consider the time factor. Hashing massive trees, traversing graphs, converting everything to SSA form, injecting phi functions, and checking for patterns takes an enormous amount of processing power.
Right, it's doing a ton of work.
When you are rapidly iterating, fixing syntax errors, and testing code, you want the compiler to finish in milliseconds. You don't want to sit staring at a progress bar for 30 seconds every time you fix a missing semicolon.
That makes perfect sense for workflow. But what do you mean by developer sanity?
I mean the absolute nightmare of debugging heavily optimized code.
Oh, because everything moved.
Exactly. Remember, the optimizer has deleted lines of code, rewritten your math, swapped the execution order, and shattered your variables into multiple unique versions.
Right.
Imagine your program crashes, and you drop into a debugger to figure out why. You set a breakpoint at line 42. You tell the debugger, print the value of X.
And the debugger has no idea what X is.
It will literally spit back the message.
Optimize out.
Optimize out. Wow.
Because X was folded into a constant and completely erased from the executable. Or worse, you tell the debugger to step to the next line of code, and because of instruction reordering, the execution pointer jumps randomly backwards to line 20. The running assembly code no longer bears any resemblance to the architectural blueprint you're holding in your hands.
The plumber didn't just reroute the pipes. He moved the entire bathroom and deleted the hallway.
That sounds infuriating. And the notes also warn that some of these optimizations can actually backfire and ruin performance if applied blindly. They briefly mention function inlining.
Ah, yes. Function inlining is a classic double-edged sword. Normally, calling a function requires overhead. You have to save your state, jump to a new memory address, and return.
Okay.
To save that time, the compiler might take the body of a small function and just paste its raw instructions directly into the loop that called it.
Which sounds great. You bypass the jump entirely.
It is great until it isn't. If the function you inlined requires several complex sub-expressions to be calculated, you suddenly inject a massive amount of new variables into your local scope.
Oh, and you mentioned the registers are limited.
Very limited. If you inline too aggressively, you run out of physical registers.
So what happens when the registers are full but the math isn't done?
The CPU is forced into a process called register spilling. It has to evict data from the fast registers and dump it back into the painfully slow main memory to make room.
Oh no, so you're back to the hour-long walk.
Worse, it completely defeats the original purpose of the optimization. Your attempt to save a few cycles on a function jump ends up causing thousands of cycles of memory delays.
It's a really delicate, dangerous balancing act.
It truly is.
And that brings us to an incredibly important point for you listening right now as you work through this specific class.
Yes, listen closely to this part.
Here's where it gets really interesting for your specific class. You are not required to implement an IR or these optimizations to get a working compiler.
Right, you can take your AST, generate raw, unoptimized assembly directly from it, and you will meet the core requirements of the project perfectly.
But if you want extra credit, tapping into Chapter 12 to add constant folding, strength reduction, or reachability analysis to your backend is the way to do it.
Absolutely. Implementing an optimizer forces you to view your software from the perspective of the silicon. It bridges the gap between abstract computer science and raw computer engineering.
And before we wrap up, let's just do a quick, friendly rundown of the upcoming tasks mentioned in the class notes so you don't fall behind.
Always good to review the syllabus.
First up, this Monday, your B minor parser for Lab 7 is due.
Get that parser working.
On Friday, you need to submit your annotations for the Liskov video. Sunday is your journal entry for week 10. And remember the 2-1 rule, minimum 2 paragraphs and 1 quiz question.
2 paragraphs, 1 question.
Finally, the following Monday, your AST decorating lab, which is Lab 8, is due. You are literally teaching sand to think right now, which is no small feat.
It is one of the most complex challenges in computer science. And as you write that parser this weekend, I want to leave you with a final philosophical puzzle to ponder.
Oh, a puzzle. I love it.
When a modern compiler uses SSA, strength reduction, and constant folding, the final assembly code often looks radically different from the source code you typed.
It's been mutated, resequenced, entirely restructured.
So, if the compiler essentially rewrites your entire logic to make it faster, who is the true author of the final executable program, you or the compiler?
Wow, it's a ship of Theseus for the digital age. If every plank of your algorithm has been replaced by the optimizer, is it still your algorithm?
Something to chew on while you debug those syntax trees.
Definitely. Thank you for joining us on this deep dive into the hidden metal. We'll catch you on the next one.